morning, everyone. Looks like we haven't met in a long time. So, unfortunately, we lost a class on Thursday. We will have to somehow make up for it. So my plan is, I want to go into the Lagrangian mechanics as soon as I can. But before that, we still have to go through certain aspects of Newtonian mechanics. Okay? So please be patient as we navigate this slightly tricky route. Yeah? Go to the Lagrangian part quickly. Okay? All right. So I'm going to continue with the problem from last time. We will solve this problem. Couple of things. You have submitted your homework assignment. Unfortunately, I'm the person who's grading it, so it's going to take some time to get back to you. Okay, probably about a week or so. Yeah. So hopefully by next week, Tuesday, I should have your homework 1 graded up with some feedback on that. Then I have to post homework 2, which will be posted sometime this week, so that you have enough time for that homework. Okay, it will be similar in terms of difficulty levels to the first homework. And I'll post my solutions to the first homework as well within the next couple of days. So a lot of things to do for me. All right. So from last time, Foucault's Pendulum. I will not rederive everything, but I'll briefly sketch out the coordinate system that we used. And then I'll list the assumptions that we made, and we will write down the acceleration expressions without deriving them because we already did that last time, and then set forth on our journey. Okay? So hopefully by the end of class today I should be done with this problem, and then I want to start talking about state variables so that we can do MATLAB programming in the next class. Okay? That's my plan. Alright, so coordinate system. Okay, so here is your Earth. We have an inertial frame that is set up at the center. We call this as I hat, some j hat, and k hat. This is your inertial frame F1. Then we had the non-inertial frame which was attached to the Earth, which was rotating with the Earth. So that's something here. Coincident with the North Pole. So this is some E1, E2, E3. The Earth is rotating about the E3 direction, or so it seems. Omega Earth was the angular velocity of this quantity. And then on the surface, at some point lambda, which is the latitude angle, or 90 minus lambda, the latitude angle. This is the angle lambda. We set up another coordinate frame to which the pendulum is attached. Okay, so this is the Z, Y, EX. And then the pendulum was suspended. P, O double prime, O prime. This was O. And we call this as frame F3. So this is frame F2. This is frame F3. And we wrote down that the angular velocity of F3 related to F1 is the same as that of F2 related to F1, which is omega in the E3 direction. So omega F3 is omega E in the E3 direction, and we split it into components along the EX and the EY, or EY and EZ coordinate system. So this is omega sine lambda EZ. Sine lambda EY. People in this line, can you see my writing here? Okay, I will stop at that point. Okay. All right, and then these are things that we wrote down. I want to very briefly look at the pendulum coordinate system. Okay, so I'm going to redraw that here. Ex, y. You see, this is the non-inertial frame. Okay. Ex, y, z. I hope you recall the frictionless pivot that I presented last time, where if the frame Ex, Ey, Ez rotates according to an inertial observer, it is not necessary that the plane of oscillation of the pendulum also rotates. Okay? They can move independent of each other with respect to a stationary observer. Okay? So here I have the following. The length L, and I'm going to take some liberties and start doing a few more things that will be useful as we go forward. I'm going to call the unit vector from the point O double prime here. This is O prime. From the point O double prime along the line of the pendulum string as E suffix L. This is some E suffix L. Okay, this is a unit vector. I take it and project it on the Ez, Ex, Ey directions. This is the angle theta here. I project it. Okay, so those will be the projections which I'll be drawing out in the darkened lines. This is the unit vector. This is 1, then 2, 3. I call this as the angle phi, and this is a plane here. Does this figure make sense to everybody? Okay, I have a unit vector EL along the line of the string. I'm taking that and I'm projecting it onto the Ex, Ey, and Ez directions. This is the projection on the Ez direction. It's pointing in a negative Ez direction, and the length of this is cosine theta times the magnitude of EL, which is equal to 1. Okay? So obviously this guy is sine theta. So if I take sine theta and then I take that and project it on the Ex and Ey, that's sine theta cosine phi and sine theta sine phi. So this quantity here is sine theta cosine phi. Sine theta sine phi. Okay, so those are the projections of the unit vector EL along the XYZ. And I'm going to write down the unit vector EL as follows, right? So EL is, you can essentially think of it, yeah, okay, let's have it right fully. So this is sine theta cosine phi Ex. Sine theta sine phi Ey minus cosine theta Ez. Okay. And from last time, first of all, are there any questions here? All good? Okay. I'm going to recall results from last time. I'm not going to rewrite this. So we had X as L times sine theta cosine phi. So which means sine theta cosine phi can be written as X by L. We did this last time. Then sine theta sine phi is Y. So that sine theta sine phi is Y by F. This is from last time. Okay? And so I can write my unit vector EL as the following. As you can see, sin theta cosine phi, so I'm going to substitute an x by L. X by L EX, y by L EY. Bring out the approximation, so I'm going to write down the list of assumptions that we had last time very briefly, just symbolically. Theta is very small. Okay, so the oscillations about the z directions are going to be very much limited, so z dot is 0, z double dot is 0, x dot and y dot are bounded. No oscillations about the z direction, about EZ. That's another assumption. Okay, then omega E is very small, so omega E square is approximately 0, and so on. Omega E square is 0. E dot is 0, and omega is very small. Okay? Alright. So with these assumptions, I'm going to say that when I see a cosine theta, theta is very small. So I'm going to say theta is approximately, cosine theta is approximately 1. So I'm just going to write this as minus EZ. We're going to make use of that. Yes?
Can you explain again why we can assume that theta is small?
Oh, we are making it small so that the angle theta does not grow very large over time. We are restricting it to be very, very small. So this is going to be a very, very, very long line, and then you're suspending it from a great height. So which means that the angle theta, as you see from the plane or the base, is going to appear to be very small.
Okay.
This line is very long.
Gotcha.
And the bob is also very massive, so there is no motion in the z direction. It's mostly oscillations in the xy plane.
Okay.
All right. I'm going to write down the acceleration expressions from last time. Okay, so this is the inertial acceleration. R double dot of the acceleration of P as seen by a stationary observer, inertial observer, are the following after a lot of approximations. X double dot from y dot omega E cosine lambda Ex, so I should say approximate, plus y double dot plus 2 x dot cosine lambda Ey, and then I'm going to have minus 2 x dot omega E sine lambda in the east. So these are the inertial components of acceleration. These are from plastic. And then we go forward with the same idea as before. We say sum of forces is equal to mass times acceleration. This is still particle dynamics in some sense. So we have not gone to rigid bodies yet. We will do that soon. So sum of forces is equal to mass times acceleration. Okay. So force, what are the forces? Tension. And then the weight, which is acting in the z direction, right? It is acting towards the center of the earth. So that's mg z. This is m times. Okay, AP stuff. All right. Tension. Can you help me write the tension force in terms of the unit vector En? In terms of the unit vector En, what is the tension force? minus t. Be careful, right? Because you are breaking the string off here. So the tension is pointing away from the point where you're cutting it off. Your gravity is acting vertically down. This is mg. This is t. So this is minus t. L minus mg dz is m times p. Okay. Okay. Substitute for EL. This is why we had written EL in terms of EX, EY, and EZ, because I eventually have to have everything in terms of EX, EY, and EZ. So I'm going to do the substitutions from here. Okay. So this is going to be minus t x by L dx, ty by L ey, negative t and positive negative Ez become plus. This is plus t minus mg Ez is m times ax m times ay. This is ax. I'm going to get rid of these. And you see the procedure is fairly similar to all the problems, right? You get the kinematics done. Yes, go ahead.
Should there be a subscript on the final t there? T minus mg should be tz minus mg?
No, no, no.
Okay.
So essentially I'm just taking EL here and multiplying this whole thing.
Oh, okay, that's t times x. T
Right,
times
right.
T
So
one.
that's
Okay.
t times minus Ez with a negative sign outside. So this is yes.
But shouldn't there be a cosine theta before the EZ?
Yes, we made an approximation that theta is very small.
Oh, sorry.
Right. So that we say cosine theta is approximately 1. Okay. And here question.
I guess to is if we were assuming cosine or sine theta is small and we approximate cosine of theta is 1, can we also do that sine of theta is equal to theta, or is that too much of a simplification?
That's too much of a simplification in some sense, right? Because you don't want to lose the essence of these terms. So you got to understand this is an approximate method. There's a lot of hand waving, a lot of shady things happening. The actual thing was an experiment. What we are trying to do is we are trying to recreate the math, shape it in some way so that you get the experimental results, and from the point of view of how the experiments played out, the results are surprisingly close to the experiments. So it warrants some of these assumptions, even though it might not look like a good one. Right? But those are all good points. And any other questions before we proceed? Okay, now things will start getting a little wrong. Alright, so now one more assumption. We'll get rid of that. Because we are saying that the bob is very, very heavy, okay, the mass attached to the end of this very, very long line is very heavy, so it is not going to oscillate about the EZ direction, so any acceleration terms there will be set to 0. And this is one reason why we say that the terms y dot, x dot are all bounded. They don't grow rapidly with time. Okay? So we're going to get rid of that guy and then just do force balance. So mass times acceleration in the x direction, I'm going to write it out. So m times x double dot to y dot or 9 lambda is minus t x by n. Okay, just mass times acceleration in each direction. Likewise, y double dot to x dot cosine lambda is ty by n. Mass times az is 0, so m times 0 is t minus mt. And something that I want to point out, if you look into the history of mechanics, physics, and so on, one of the characters that you'll come across is Enrico Fermin, right, the nuclear physicist. And in some sense, I like his philosophy, where he says that the experiments, he was an experimental physicist to begin with, but he was equally well versed in theory and all that. And his philosophy was the experiments are closer to the truth than the theory. So you can tailor the theory so as to make any kind of an assumption to get the answer that you want, that you experimentally observe. And in some ways, this is exactly what we are doing here. We are saying that, okay, we have all these things. This itself is a huge approximation to begin with. And on top of that, I'm making other layers of approximation. Is it valid? The validity comes only when we look at the final results of the analysis and see that this approximates the experiments in a fairly nice way. Okay, so that's where we are heading towards. Yeah? I strongly suggest reading about Enrico Fermi. Unfortunately, Feynman and Einstein were the more famous of the scientists during that era. Fermi got a very bad end of the stick, and he also died very young, I think 52, 53. So he was not as much seen on TV or radio during that time. Oppenheimer was another big figure during that era, the Manhattan Project and all that. So very interesting people. Okay? Their thinking is very different from regular human beings like me. Okay. So m times 0 is gone, which tells me that T is equal to mg, so this is great news. So I can get rid of the tension, substitute it equal to mg. Right. So this is an order of magnitude analysis. So T is equal to mg approximately, which means wherever I see a T, I'm going to substitute for mg. So that's going to happen here and there. So m times x double dot 2y dot omega e cosine lambda is minus mg x by L. Likewise for y double dot. Cancel the mass on both sides. Does this term G by L ring any bells? Yes?
Potential energy?
Potential energy, not really. This is, well, let's look at the units. Okay, so D is m times mass times second square. This is L is in length. 1 by second square. If I take the square root, 1 by second is the free is what?
Hertz.
Hertz multiplied by 2 pi. Frequency of oscillation. Square root of G by L is the frequency of oscillation, magnitude of that of a simple pendulum. Okay, so I'm going to call the term by a different name now. So G by L, I'm going to call it as omega naught square. So it's some frequency of oscillation square. And so immediately you recognize that this is a problem on 2 time scales. You'll see this as we do the solution. There is a fast time scale because omega naught is much faster, that is dependent only on the geometry of the pendulum, right, the length of the pendulum. And then there is this very slow spin that is taking place, which is a spin of the earth. So there is some very slow event that is taking place, and then there are some very fast events that are taking place on the thing that is spinning slowly. So that's very weird here. Yeah? So I'll do the substitutions and we get the following. X double dot minus 2 y dot omega e cosine lambda is minus omega naught square x y double dot 2x dot omega e cosine lambda, same stuff. Omega e cosine lambda is minus omega naught square. Now we want to solve this equation. It's a coupled oscillator, essentially. It's a coupled system of differential equations. There will be several tricks that you learn in this course to solve things of this nature. Today's is the first trick. Some of you may have come across it, but you do the following substitution. So our aim is to solve these for x of t, y of t. What is x of t, y of t? X of t, y of t is the position of the pendulum as seen by a non-inertial observer. An observer who is sitting in the frame EX, EY, EZ. Okay, so I want to write that down here. With your permission, folks on this side, I'm going to write it down here. Okay? The x of t, y of t, the position of the pendulum seen by a non-inertial observer. You see that I break my promises many times. So we do the following substitution. Okay, so we say some s is x plus I. This is a trick, completely purely a trick. There's no physics behind this. Okay. The real part of s is x. Imaginary part of s is 1. So if I need x, I will look at the real part of s. If I need y, I will look at the imaginary part of s. Okay? So if I have this, I differentiate both sides. I is the imaginary number, so that's something to keep in mind, and I square is minus 1. S double dot, x double dot, and y double dot. Substitute into those two equations. Okay, alright, so if I do the substitutions, here is what I end up getting. The x double dot. Instead of, I'm going to substitute for x double. Okay, let me do that. That should be more clear. So x dot is s dot minus iy dot. X is s minus iy, and so on. And x double dot is x double dot. So these are the ones that I'm going to be substituting. Write that here. So instead of x double dot, I'm going to have s double dot minus iy double dot. Please notice, I'm doing the substitutions in the first one. Okay, that's the first set of substitutions I'm doing. So wherever I see an x double dot, I will substitute in terms of s and y. You can do it the other way as well. Wherever you see y, you can substitute in terms of s and x. That's not right. Then minus 2y dot omega e cosine lambda. This is minus omega naught square. Can I get rid of all of this? Okay. I just want to have some space, so I'm going to get rid of this, just this. So that's minus omega naught square times s. And then plus omega naught square times I times 1. Okay, because I substituted s as s minus I. Likewise, y double dot plus 2 times s dot omega e cosine lambda plus minus 2i y dot omega e cosine lambda is minus omega naught square. Okay, so these are the two equations that I have. I'm going to take the second one multiplied by the imaginary number I. Okay? So take the second one, multiply by I on both sides, and then you'll see what happens. So I'm going to write the first one again. Is double dot y double dot minus 2 y dot omega e cosine lambda is minus omega naught square s plus I omega naught square y. That's the first one, nothing happened to that. Second one, I multiply by I, so I y double dot. Then I'm going to have 2I omega e s dot cosine lambda. You see what I'm doing? Then I keep going forward. I times I is minus 1, but I have a negative sign, so this becomes a plus. Okay, when I write the next one. Okay. So this is now going to be plus 2 y dot omega e cosine lambda. This is minus I omega naught square. Add these two up, the y double dots, y dots, and the y term will cancel. I will have a differential equation only in S. So add these, this is gone, this is gone, this is gone, that is also gone, this is gone, that is also gone. Okay, so here is my equation. This double dot plus 2 omega e cosine lambda is dot minus omega naught square s. I'm just bringing it to the other side, so it becomes plus omega naught square s is 0.
Yeah, that's how I do it.
Once again, this is just a trick. It is a question.
It just, I noticed that looked like a mass damper system.
Oh, absolutely, with the imaginary term.
Yeah.
Yeah. So we are going to use the same idea as you do for a mass damper system, have a trial solution and then solve. So the solution is going to have real and imaginary parts. If you want x of t, you take the real part. If you want imaginary, you take the imaginary part, you get y of t. That's it. It's just a trick. Okay, there is nothing to it. Unfortunately, there is no physics behind it, but we need it for the physics. So you would have come across trial solution methods and so on. So that's typically what I'll be doing. A solution that is kind of an exponential function of time. Okay. So select S is e to the power I beta t, where beta is still an unknown method of coefficients, or whatever you want to call it, undetermined coefficients. The beta is still unknown. We need to solve for beta. Take the first derivative and second derivative. S dot is I beta t. S double dot is minus beta square I beta. Why am I taking e to the power I beta t is because, as you rightly pointed out, this is like an oscillatory equation, right? So if I take e to the power I beta t, and if I make use of Euler's identity, I will get cosine and sine terms. And that automatically implies that there is some oscillatory behavior that we would like to filter out and remove from the system and understand it better. Okay? That's the reason why we're doing it this way. It works for any spring mass damper system, by the way. All you need to know is the spring mass damper system, if it is linear, that's the solution. E to the power I beta t. Or e to the power beta t, if you have a real system. Alright, so do the substitutions. You need to solve for beta. S double dot is minus beta square e to the power I beta t. Then I'm going to have S dot, which is I beta e to the power I beta t, but I already have an imaginary I next to the second term there, so that's going to be minus beta e to the power I beta t. Last one is just omega naught square. I'm missing out on omega e over lambda, then so I can take e to the power I beta t as a common factor, remove it out, and then set that equal to 0, which is going to give me a trivial solution. So I can cancel off all of these. That's not going to help my problem. So now I solve for beta. It's a quadratic. Okay? So I can solve for beta. So beta square. What's this? This guy. I'm just going to call it as some capital omega. Okay, what is this? Cosine lambda is just some shifting factor, right? So this is just omega is omega e cosine lambda. So plus omega beta minus omega naught square quadratic, two roots. So beta is minus factor of 2, I'm sorry. I missed out on that. It's a 2. So minus 2 omega plus or minus square root of 4 omega square, right? Plus 4 times omega naught square. That negative sign there is a lifesaver. Otherwise, we would end up having imaginary roots for an imaginary expression, which is not going to lead us anywhere. So this positive sign is because I have a negative sign there, divided by 2. These are the two roots, right? Typical roots. Cancel. Omega square. What did we say of omega square? Capital omega square. Approximately 0. Because omega of the earth is very, very small. 10 to the power minus 5 sometimes. So this tells me beta is minus omega plus or minus omega naught. We get rid of that omega square term because omega e is very small. So we say alright. So two roots, which means if I write my solution, I'm going to have two constants, right, which will come from the initial conditions. Okay, so I'm going to have S of t is, let's call this as beta 1 and 2. So this is C1, some linear combination of the two roots, right? So C1 e to the power I beta 1t, C2 minus I beta 2. Okay, so beta 1 and beta 2, I'm just going to do the substitution. Bear with me while this is a slightly boring step. We do the substitution, use Euler's rule, identity, and then write down everything in terms of cosines and sines. We just need to do it once. So C1 and this is, instead of writing E, I'll write exponent so that I can write everything more clearly. This is exponent of minus I omega t plus I omega naught t. I'm substituting for the first root, the positive one. The second root will be the negative one, plus C2 exp minus I omega t, and that's going to be minus I omega. Euler's identity. Before that, I can do the following. E to the power a plus b is e to the power a times e to the power b. Right? So I can factor out one of these things. So this is a common factor here and there. So this is e to the power minus I omega t c1 e to the power I omega naught t plus c2 minus I. So you see now the fast scale and the slow time scales. The fast time scale is omega naught times t, because omega naught is an order of couple of orders of magnitude, maybe a very large order of magnitude greater than the spin of the Earth. This is something that we control. If I have a very short length L, then my omega naught is going to be small, very high. If I have a very long length L, it's going to be small, but it's still going to be larger than the omega of the Earth. The slow time scale comes from here. Okay, this is omega times t. So this is a problem of multiple scales. Expand it out. E to the power I theta is cos theta I sin theta. I'm just going to write the formula and then write the final expression. I don't think we want to waste our time expanding it here. Cos theta minus I sin theta. Okay. Maybe do one expansion. This is cosine omega t minus I sin omega t. That's the expansion of the first exponential term. Then the terms inside the brackets. Okay. So I have c1 cosine omega naught t I c1 sin omega naught t plus C2 minus I C2 omega. Alright, so we're almost there. So what we're going to see here is if I take all the real terms from here, the real terms coming from the fact that I have to take cosine omega t, multiply with that guy, multiply with that guy, then I have to take sine omega t, multiply with that and multiply with that. So that the I times I becomes minus 1 and the appropriate sign becomes the following. So S of t, real S of t, which is x of t, is the following. So this is C1 plus C2 cosine omega t omega naught t, and then C2 minus C1. Sin omega t sin omega naught. do the multiplication, take out all the real terms, set that equal to x of t. Do the multiplication, take out all the imaginary terms, set that equal to y of t. Okay? Y of t is imaginary s, and this ends up being the following. So this is going to be, I'm going to have C1 minus C2 cosine omega t and so on. So C1 minus C2 cosine omega t sine omega naught t. Then I'm going to have C1 plus C2 with a negative sign. So minus I, so that's minus C1 plus C2 sine omega t omega naught t. All right. All of us are on the same page. What's my plan? Not to. This is all just a distraction. Okay, writing these equations is just a distraction. Our plan is to solve for x of t, y of t, which is why we did all these tricks, and then we obtained the solution that we want, and to figure out and see, okay, what is the motion of this pendulum system, okay, from the perspective of a non-inertial observer. So to make the problem a little more simpler, just to imagine it in our heads better, okay, I'm going to say we are at the North Pole. So for us, cosine lambda becomes equal to 1 because lambda is 0 at the North Pole. Technically pi by 2 minus lambda is pi by 2. Doesn't matter. So this says that omega is omega of the Earth at the North Pole. And to find C1 and C2, this is completely dependent on your initial conditions. That is, you prescribe. Okay? So I'm going to say that initial conditions, as seen by a non-inertial observer. Okay, so I'm sitting on the Earth frame and I'm giving the pendulum some initial conditions. X of t is some constant. Y of t is 0 at t is equal to 0. So these are my initial conditions. And I'm going to take some liberties here. You're going to actually show it in the next homework assignment. You will see that the initial conditions completely satisfy the equation. There's no doubt about it. Okay? You'll have to make some assumptions though when you do the substitution of the initial conditions. Okay? Because when t is equal to 0, it's 0 here, it's 0 there, so you cannot solve for C1 and C2. You see, if I look at y of t, when t is equal to 0, both of them are approximately 0. So we have to make some assumptions there to solve for the constant C1 and C2. I'm going to leave it to you. And I'm going to tell you that based upon these, hand waving, okay, for purposely hand waving, C1 is, C2 is equal to each other. This is what you'll end up doing after making the assumption that omega is much less than omega naught. So this is an order of magnitude assumption once again. You make that assumption, you solve for C1 and C2, then you go back to your main x of t, y of t, substitute, and obtain your x of t and y of t. Okay? So x of t will end up being a times the first term, cosine omega t, cosine omega naught t. Y of t will end up being, watch this, these conditions are chosen carefully so that I end up with minus a, okay, because C1 plus C2 is equal to a, so this is minus a times sine omega t cosine omega naught. Okay. Now we want to look at the motion of the pendulum as time progresses. Right? So let's draw this figure here. Okay, so this is the x-axis. The x, the y. What are we observing? We are observing the motion of the pendulum from the non-inertial perspective, non-inertial observer, right? So when time is very small, when t is very small, it is possible for me to look at these two and then simplify and say that this y of t is not going to play much of a role, right? When time is very small, sin omega t, cosine omega naught t, sin omega t is going to blast it off, so that's going to be approximately 0. So I'm going to have x of t approximately equal to a times cosine omega naught t. Y of t is approximately 0. Do you all see my assumption here, and you see why this comes about? When time is very small, cosine omega t is approximately cosine of 0, so which is 1. I cannot do the same thing here because omega naught is an order of magnitude larger than the omega of the earth, right? So I cannot make the same assumption that this term is also approximately 0. And I'm not saying that this is at time t is equal to 0. It is at small time. Question?
Should there be a plus sign then between the a and the cosine for x?
Which one?
For x of t, your approximation. Because if cosine omega goes to 1, how are you multiplying a by cosine omega naught t?
Right. So this is not this is a t. This is a t. Is that?
Yeah. You said that term went to a times 1, correct?
This term goes to a times 1. Right.
Oh, that's a t.
Right.
Okay.
So,
got it.
so what I'm saying is when time is small, this term is approximately 1. This term is approximately 0. I can't make any judgment on these two terms. Okay, because omega naught could be a large enough value, so that the magnitude of omega naught times t is sufficiently large. Okay. But what this tells me is that for a very small time, if I had a pendulum suspended from here, what it would be doing is it would just be oscillating about the x-axis. Right? You see, it is just going to be doing the following. Somewhere here, it will just be oscillating back and forth. Okay, this would be the magnitude of the oscillation, or amplitude of oscillation A. This is at very small time. Am I making sense to you? Now let's say that the time is not small, but it starts kicking in. Okay, time becomes sufficiently finite. What's going to happen is that the oscillatory motion is going to be a combination of motions along the x-axis and the y-axis. For positive oscillations, I'm going to be sitting at a positive x value and a negative y value. So I'm going to be sitting somewhere here. And the oscillatory motion will just proceed along in that particular direction. Okay, so it is just going to be this way. Does this make sense to everybody? And as time keeps going further and further, I will see that this is now going to start doing the following. It will come somewhere here, and then after one full day, it will come back to the x-axis. And so you see that the plane of oscillation, which is this xy plane, this is precessing in the clockwise sense. So I'm going clockwise, and this plane travels one full oscillation or one full rotation in one day. So which means that its angular rate is the same as the speed of the Earth, but in the clockwise sense. Okay, so this is now going to be rotating this way. So this is omega e. So if I call this as a plane P, so omega seen by a non-inertial observer is clockwise. So that's going to be minus omega in the EZ direction. But remember, we are at the North Pole where the EZ and the E3 are the same. Okay, so EZ and E3 are the same. So this is minus omega of the Earth E3. Is everybody seeing the clockwise motion? Okay, as time progresses, you're essentially what you're doing is, for a finite time, you're freezing these two quantities. They don't oscillate by too much. So if I'm looking at some finite time, my x of t is approximately a times cosine omega t. My y of t is approximately minus a times cosine omega t. So that if I'm starting at a point on the negative y and positive x, and I'm oscillating between there and a point on the positive y and negative x. So that's the direction of oscillation for me. This is for a finite time. Okay? And when I say finite time, it means that I'm increasing very slowly in time so that these omega t terms don't play too much of a role. Okay? There's just going to be some constant values at that instant in time. So there's going to be some slight shift taking place, but broadly speaking, this is going to be the direction of rotation. Okay? Makes sense? Yes.
When they did this experiment back in whatever year, how are they able to manage to reduce friction enough to be negligible?
That is a good question. I mean, so the design that Foucault came up with was something similar to what I showed you, where he had a very smooth hemispherical shaped contact. And there is obviously the possibility of friction. So it must have been a very carefully thought out experiment.
Okay.
Yeah. I don't know the exact details of it, but I can get back to you on that. I think there is there could be. I'm not sure. So there are a couple of books on history of mechanics, but they don't talk about this particular experiment. But I can check it up and let you know. We'll get back to you. Yeah, the exact experimental apparatus. But there is a possibility of friction playing havoc on this. If we try this at home, obviously it may not be successful. So I must digress here. So this is my point, is that the plane of oscillation is rotating clockwise. And so we make the final argument. That's my eraser. So if you go back to what we spoke about in the last lecture, which was some time back, I think this was my setup. This some kind of a hemispherical stuff, so smooth contact is smooth and frictionless. Here is the pendulum. This is sitting on the frame of the Earth. So if I'm an inertial observer and if the pendulum is oscillating, the plane of oscillation of the pendulum will not be moving according to an inertial observer. Okay? So omega of the pendulum plane of oscillation with respect to our inertial frame is 0. Because the motion of the pendulum is independent of the oscillation of the pendulum is independent of the rotation of this frame here. All we are trying to see is, okay, if I'm sitting on this particular frame, how does the pendulum oscillate? Omega of t with respect to f3 is minus omega e3. And so if I now bring the equation, omega p slash f1, p slash f3, f3 slash f1, this is your typical addition of angular velocities. This is 0, is minus omega e3 plus f3 slash f1, so plus of course, this is quite sketchy, right? In the sense that we started off by saying the Earth rotates and then we are proving that the Earth rotates. So it's just that the means, ends justify the means in some way. But the physical proof is from the experiments. So if that physical proof is there, then the math just goes to show that we are right in making these assumptions and coming up with this final result. Okay? So that's where this ends, the so-called pendulum. And I suggest, maybe going to COSI if you haven't been there, take a look at it, spend some time looking at it. One might have a good idea of how these things work better, yeah? Physically speaking. Okay. So now I want to move on. We have around 15 minutes left. I want to talk about 10-15 minutes left. I want to talk about state variables, the state space method. Many of you may have come across it in system dynamics. So for that I apologize. There might be some redundancy in what I'm speaking about here. Okay? But I think I still want to talk about it. State variables. The reason for doing this is because I want to set up differential equations in math. Okay? Of course, that's not the reason for their existence. MATLAB came after all these things were thought about. The idea is that if I express equations of motion in the state space representation, it's a very nice way of reducing the complexity of my calculations. It is all going to be done using vectors and matrices. So that is how MATLAB thinks. MATLAB thinks in the language of vectors and matrices. So this gives us a good way of representing equations. Okay? So I'm going to look at a simple example. Just a ball traveling along the horizontal plane. Okay, so let's say this is x of t is its degree of freedom, right? And I have some forces acting on this ball. And from basic vector equations and using Newtonian mechanics, we can say that the mass times acceleration is equal to the force. Doing rectilinear motion, so acceleration is going to be in the x direction, the horizontal direction. There is no surprise in this one. So acceleration is F by m. So, what is the question that we want to ask ourselves is the following. What information do we need at time t naught at some time t naught so that I am able to predict the configuration of the system at the next instant in time? System configuration at the next instant t. And when I say what info, I say what is the minimum information that we have. If I have more information, I can certainly live with that, but at least what is the bare minimum that I have? What is the configuration of the system? The configuration of the system is what is its position, what is its velocity. Okay, so that is the system configuration. This is typically for us in dynamics. Okay, if you do mechanics of materials, deformable mechanics and so on, the word configuration and what are the quantities that pertain to the configuration have a different meaning, slightly different. Okay? For us, we need position and velocity. I have acceleration from Newtonian mechanics or from Lagrangian mechanics, whatever framework you choose. Does not matter really. So from the acceleration, dv by dt, right? So that dv is a times dt. I'm going to integrate between the time t0 and t1. And this is fairly trivial integration on the left hand side at least, not on the right hand side. So this is v at t1, v of t0 is integral a dt. I can perform that integration on the right hand side if I know force is a constant. That is basically trivial nonsense. If I know that the force is really complicated, we have numerical methods. No problem. Can solve anything with some degree of certainty. So to find out the velocity at the next instant in time, the important piece of news that I need is I need the velocity at the previous instant in time. Okay, so that's my first state variable. Okay. I need to find the position as well, so I integrate the velocity. So dx by dt is v of t. Just integrate on both sides, do the same thing as we did here. X of t is t0 integral t0 to t1 v of t dt. So now we come to an important distinction. You see, when I said I wanted to know the configuration of the system, I said position and velocity, and now you see that there is a triviality, there is a redundancy there. I actually don't need the velocity. To know the configuration of the system, I need only the position, because that is the barest thing that I need to find out. Okay, so I need only the position. I don't need the velocity. The big deal is, why is this true? Why don't I need the velocity to know the configuration of the system? Is because to know the position at time t1, what are the things I need to know? X at t0, I need to know that. Then I need to have v of t dt, where v of t is a function of the initial velocity v of t0. And then this comes from Newton's law and some integration. So there are three things I need to know. Newton's laws or the framework for solving systems of equations, which is Lagrangian or Newtonian mechanics. Then I need to know the initial velocity or the velocity at the previous time instant. And I need to know the position at the previous time instant. So these variables that I need to know at the previous time instant, the minimum number of variables I need to know at the previous time instant to say what's going to happen at the next time instant is just 2, which is the position at the previous time, the velocity at the previous time, and this is called deterministic mechanics. Newtonian mechanics is deterministic. If I know the information regarding position and velocity at the previous time instant, I know everything about the problem as it moves forward. Okay, so when you talk about chaos, right, we will talk about chaos towards the end. The chaos that we talk about is deterministic chaos. It is not something that you see. I mean, people say turbulence is chaos, or you can have chaos in stochastic dynamics and so on. Those are all probabilistic events. Statistical thermodynamics, you can have chaotic systems there. Those are all different types of chaos. They are not the chaos that we study in dynamics. We study deterministic chaos, which tells me that if I know the initial conditions exactly to the millionth, whatever the infinite number of decimal points, then I know how to predict the system evolution for a very small change in initial conditions. Okay, but we unfortunately don't know that. We are not privy to that information, and so certain systems behave weirdly. Maybe just to not talk too much, the final point I want to make here is what are state variables? The minimum number of variables you need to know at the previous time instant, so that you know the configuration of the system at the next instant. Okay? So if I have a second order ordinary differential equation, which is what is this trivial problem, the ball sitting on the ground is x double dot is f by m. So the number of state variables I need are 2. I need the velocity and the position. Okay? So those are called state variables for us from now on. So the state variables for a system x double dot, which is a function of all of these. This is just an ordinary differential equation, second order ordinary differential equation, 2 state variables. Position, velocity. So for one second order ODE, I have 2 state variables. If I have 2 ODEs, I'm going to have 4 state variables, and so on and so forth. And what's the utility? The utility is that we can make use of this in a state space representation of dynamical systems, which will be a very compact way of presenting the equations. Okay? So for example, the state space representation. Once again, I believe you would have seen this in system dynamics or some kind of a course of that sort, but it also is a function of who teaches those courses. So I'm just refreshing your memories. Okay? So state space representation, let me just take a simple equation. X double dot is minus g by m. It's some equation, random equation. Second order ODE, so I have 2 state variables. X of 3, x dot of 3. I'm just going to call them as the following. I'm going to call this as some x1. Okay. Then I'm going to call the second one as x2, which is in reality x1 dot disguised as x2. Right? Does this make sense to everybody? And so if I write the system, the state space representation of the system is a set of first order ODEs. Give it a short form, state space representation. SS is a set of first order ODEs in the state variables. They may be linear or non-linear, these ODEs. We don't really care about that. Non-linear, more fun. Alright, so then I have my first state ODE is already written there. X1 dot is equal to x2.